I am Masaru Watabiki, Toshiba Digital Solutions Corporation, but I am here today acting Q-Star chairman of the executive committee, Okada-san. I'm not good at speaking English, so please allow me to present with the script. Okay. At first, I would like to briefly introduce myself. In 2019, I took on the business development of the quantum-inspired optimization solver SQBM Plus, and 2021, I was also responsible for the business development of the Q2B business. In the same time, I was invited by Q-Star to participate in the following subcommittees and working groups, many groups. Before introducing Q-Star, I want to take a brief look at where we are heading. I think of the past 10 years as the first step to the future, the transition from cyber to cyber, DX 1.0. This has seen GAFA establish something like a Benjamin. Now we are seeing growing interest in combining cyber technology with data from the physical world. At Toshiba, we call this DX 2.0. The huge change that will follow this, brought about the quantum technology, will drive quantum transformation, QX. Quantum technology is advancing much faster than predicted. In the 80s, it was widely believed that realizing the qubit would take 100 years. But 10 years later, it arrived. For example, last year, IBM announced its new 127 qubit Eagle processor and promises 1,000 qubit computer by 2023. Google plans to launch a quantum computer by 2029. Many companies are now working on ways to increase the number of quantum bits and advancing plans to realize fault-tolerant quantum computers by around 2030. Last September, Toshiba researchers achieved a breakthrough in quantum computer architecture, the basic design for a double transom coupler, a key device in determining performance. The technology is expected to advance the realization of higher performance quantum computers that will contribute in such areas as the achievement of carbon neutrality and the development of new drugs. Quantum computers are roughly classified into two types, Ising types and gate types. Ising types, also called annealing types, are dedicated to solving combinatorial optimization problems. Gate types are universal and they are expected to run various algorithms. The Ising type D-Wave 1 was developed by D-Wave Systems and released in 2011, when it was considered too early to release quantum computers. Ising types aim to solving various large-scale combinatorial optimization problems, which are difficult to solve quickly on conventional computers. In relation to Ising-type quantum computers, practical use of algorithms that are quantum-inspired is increasing. This kind of algorithm emerged from studying quantum computers but can be executed by conventional digital computers. Various methods are being applied to development of universal gate-type quantum computers. The multi-purpose ones, including superconducting circuit, semiconductor, quantum dots, light ions, and atoms, and the most likely method has not yet been fixed. Here is a brief presentation about Toshiba's quantum-inspired optimization solution, SQBM+. A quantum-inspired optimization solution that can be used immediately in public cloud environments such as AWS, Azure, and commercial FPGA environment. We are currently consulting with various users and partners to explore use cases that can contribute to solving many social issues. More details will be presented by Izumi-san from Toshiba in the quantum hardware software track at 16:10 minutes after this. Please come and listen to the presentation. This slide, the potential quantum computing market, is taken from McKinsey, the Quantum Technology Monitor. As you can see, in 2025, the market size is predicted to reach the range of $12 billion. And in 2030, it will double in size with the possibility growing to $28 billion. Now, quantum technology is developing at the learning rate. It is said that when the quantum computer is fully developed and available, then current mathematical type encryption technology will easily be breached and broken. Toshiba is a leading manufacturer of quantum cryptography, a communication method that prevents theft from conventional type of encryption. We are convinced that a time will soon come when our communication will be protected by the quantum. Looking to the future, in October this year, the Chicago Quantum Exchange, one of Toshiba's partners, used our QKD in a mock election for Chicago high school students. By voting, students experienced participation in a real-world application of quantum technology. We hope that inspires them to become members of the future quantum community, and we believe opportunities like this are important for nursing talent for the QX era. Moving on from the QX overview and Toshiba's works, I will now put on my hat as a member of QStar. QStar, Quantum Strategic Industry Alliance for Revolution. QStar was established in September 2021 to create industries and businesses based on quantum technology. Membership is open to both large and small companies, including venture companies, startups, and to academia. Our scope of coverage is very wide, from quantum computers, data, Q2B, and application software to materials and devices, medicine, biotech, sensors, and AI. Here's a board member. Our 9-member board draws from large and small companies, users, and vendors. We started with 24 members and now have 62 with a good balance of vendor and users. This creates a suitable environment for identifying use cases with high possibility of realization. I believe significant momentum is now building for the promotion of quantum technology. Reviewing the first year of Q-Star, I see progress everywhere, especially here in Japan. Q-Star was launched in 2021 and collaboration with industry consortium in Europe and the US, which are leading the way overseas, is now underway. R&D of quantum technology, including the development of domestically produced quantum computers, is highlighted in the Kishida administration's new form of capitalism. Q-Star participated in the review working group, which is a companion piece to the quantum technology and innovation strategy. One of Q-Star's notable achievements in our first year was the implementation of our proposal in Vision of Quantum Future Society, published by the Cabinet Office as a vision and goals for future society. In line with our proposal for the vision of quantum future society, we have 4 policy goals. Number 1, build a society where quantum technology supports us all. Advance the technology at a global level. Number 3, speed up its adoption. Number 4, and use our position to initiate activity. Q-Star incorporated just this May. This broadened our scope of activity, and we aim to contribute as an opinion leader at the global level. The executive committee has 8 working groups covering the theme you can see here. The work and recommendations of the top 6 were incorporated into the vision of quantum future society. But legal compliance and human resource development are new, set up to meet demand as Q-Star activities evolve. For many members, the main reason for joining Q-Star is participation in subcommittees and working with our diverse membership to create use cases. We now support subcommittees working in the 5 areas you can see here. All the subcommittees are now identifying use cases to explore in areas that include finance, quantum chemistry, calculation, logistics, energy, medical, information platform, and more. I think the other major accomplishment of our first year was Q2B, the quantum reference architecture model for industrialization. Q2B was inspired by RAMI 4.0 as a model for viewing quantum business. We aim to use it as a global tool, a platform for common understanding. For example, this is quantum psychology and quantum communication subcommittees. When we built that in Q2B to see the overall image, this was the result. This is more example. This is an example from our subcommittee discussion on quantum psychography and quantum communication technology application. Orange line is NDA, sorry. You can see here how we use Q2B to identify long-term goals. As I said, one of our policy goals is to advance progress and application of quantum technology through international cooperation. We have been communicating in workshops with the consortium you see here. We are working closely with all of them, especially QEDC, QUIC, and QIC, and discussing supply chain mapping, Q2B, export control, and other shared issues and common interests. In our global activities, we are especially keen to build up a map that allows us to grasp the status of the quantum industry's global supply chain. This will help us to understand the strengths and weaknesses of Japan's quantum industry, keep up with changing trends, create guidelines for industry development, and understand supply chains that can be established under export control measures. Sharing this globally will also allow Japan's quantum industry to expand its activity overseas. Last slide. We understand the value of industry events like today's and participate proactivity. Through close cooperation with domestic and overseas institutions and organizations, QStar aims to accelerate implementation of our use case in global society. Thank you for listening.